So this talk is titled Byzantine Channels and Systems. And this work is motivated by distributed systems. So as we know, distributed systems are everywhere. For example, file system, cloud storage, blockchains, Internet of Things, and so on, right? And what we require from a distributed system is to make sure that even if some of the nodes are malicious, the system continues to function, right? And by the way, what is a distributed system? These are a bunch of nodes which are interconnected through a shared communication medium, right? So if there are some faulty nodes, they can try to mess up with communication between honest nodes, okay? Currently, all this security is actually tackled at the application layer of the system, whereas raw bits are transferred at the physical layer. In this work, what we try to do is to bring the security all the way to physical layer. Okay? And if you think of it in terms of evolution of information theory, starting from the work of Shannon, where point-to-point communication was looked at, and in the last couple of years, we made huge progress in network information theory. What we need right now is network information theory, which also accounts for nodes which are malicious, so that it can be applied to most of the systems which are currently run, right? And this is the work that we look at over here. So we look at fundamental limits of communication where users may be malicious. All right, so what we are interested in is Byzantine broadcast and Byzantine multiplexes. What does it mean? This means that these networks are allowed to have nodes which are malicious, okay? And there are honest nodes in the system as well. They are not aware of the identity of the malicious nodes. There may or may not be any malicious node, okay? So I'll formalize all of it in a bit, okay? So in the Byzantine multiplexes, we study 3 different guarantees. And in the broadcast model, we look at common message broadcast under 2 different guarantees. And if there is more time, I'll discuss one of them in more detail. So this talk is going to be overview of a class of models, basically these 5 models. And I'll discuss a bit about details of these models. Yeah. All right, so let's start with Byzantine multiplexes channel. So in order to motivate it, let's look at a smart home. So what is a smart home? It has all sorts of devices like locking system, some stereo, TV, lighting system, and so on. They're all talking to each other through a shared internet. Okay? And suppose one of the device malfunctions or gets hacked. We want to make sure that critical devices continue functioning. That is, even if there are malicious devices in the system, we're able to provide communication to important devices. This is what we call reliable communication. On the other extreme, if there are non-critical devices, it is okay for them to gracefully shut down. And this is the here, if there is a malicious device, these devices can be like, okay, I can't provide functionality because there's a malicious device in the system, so that they don't cause any errors, okay? So this is the other extreme. We also study an in-between model, which is called communication with adversary identification. Here, the devices are allowed to shut down while declaring the identity of the malicious user. So it's like, oh, I can't function because this specific guy is malfunctioning, okay? So what does it mean in terms of modeling on a multiplexer channel, okay? So let's recall, what is a multiplexer channel? There are multiple senders and a single receiver. And the channel is given by a conditional distribution on the output alphabet conditioned on the input. Okay? For example, a Gaussian multiple access channel where the output is the sum of inputs plus additive Gaussian noise, or a binary additive MAC where the output is XOR of the inputs. How does communication happen over a MAC? Messages are encoded into code words and sent through the channel in a DMC fashion, memoryless fashion, okay? And we are often interested in the capacity region. So what is the maximum rate at which we can support communication for all the users? So this is multiple access channel. We want to study a Byzantine multiple access channel. What does it mean? This means that some of the users here could be malicious. For example, in a 2-user multiplexer channel, user A over here is malicious. What is the meaning of a malicious user? This user may not send a valid code word. And in fact, this user is allowed to send any n-length sequence from the alphabet. On the other hand, the honest user will be following the protocol and will be sending a valid code word. Okay. And receiver does not know if there are malicious users and who is malicious if there are any. Okay. Again, when everyone is honest, we want reliable decoding. So the decoder should output the messages of all the users, right? And if there are malicious users, depending on the model, there'll be different requirements. So the first model, which we called authenticated communication, which is the weakest model, this requires that if there's a malicious user, the decoder should either output a pair of messages of which the message of the honest user is correct, okay, or the decoder should flag that, oh, there's an adversary, okay, and we cannot communicate. So at this point, I'll stop. If there are any questions, do you understand the model? Does it make sense? Okay. All right. So in this model, our goal is to characterize the capacity region of this channel. Okay. And turns out that for this problem, the capacity region is same as the capacity region when both users are honest for most of the channels. So there's a class of channels where you cannot do anything, but turns out whenever you can do something, you can actually achieve the entire capacity region. And this is obtained by, the code looks something like this. So there's a communication phase, which is a typical MAC code that we use here. And then there's a further authentication phase, which is of very short length, so it doesn't add to the capacity. And this authentication phase will help us in sort of flagging that there's an adversary. And the reason the authentication phase is really small is because this is actually based on identification codes, which allow doubly exponential rates. So we can make it really short. So yeah, this is all I'll say about this model. And if you find it interesting, you can look at the paper. But let me move on to the next model. Here again, when there is no malicious party, both users messages are decoded correctly. But if there are malicious users, we want to make sure that the functionality is provided for the honest user even in that case. So the decoder should always output a pair of messages of which the message of the honest user, MB, for example, over here, is correct. Okay? So this is the most stringent guarantee. Okay? So let me try to give an intuition of the rate region for this specific channel. Okay. So if we think of this channel, this can be thought of as an AVC if user A is malicious. This is like an AVC. What is an AVC? It's an arbitrarily varying channels where there is an adversary who can vary the channel, like jam the channel. Yeah? So if a malicious user can behave like an AVC, and so you cannot do anything better than that. At the same time, you can actually use an AVC code for this specific user and achieve this sort of rate point, right? And the same argument also holds for this other user. So this square is the capacity region for a 2-user MAC with reliable communication. What we do in our paper is actually we look at k users out of which any t could be malicious and what happens over there. So that would be an extension of all these arguments and requires coming up with new coding theorems and so on. But yeah, here again, we'll have to look at the worst case attacks for these kind of problems. All right, so that was the second model. And this is the third model. Here, this is called communication with adversary identification. So this is like an in-between model. Here, if there's a malicious user, the decoder should either output a pair of messages of which the message of honest user is correct, or the decoder should say, okay, this specific user, for example, user A over here is malicious. And for this problem, we give capacity region upper and lower bounds. And we also show sort of strict containment that one capacity region is into another and so on. So we give some examples and so on. So this is all I wanted to say about the MAC problem. Let me know if there are any questions about it. All right. So this problem was about studying multiple access channels when some of the senders could be malicious, right? And what we looked at over here was capacity regions of different models. And one of the capacity region which is still open is this adversary identification kind of model. So that is a future direction. And we only give capacity regions. We did not come up with efficient code. So that's another thing if you want to actually implement these kind of problems. And we only looked at finite alphabet in all these problems. So Gaussian channels or like others, these kind of channels are still open. All right. So, okay, so this covers the multiple access channel part. Let me, in the last 10 minutes, I'll try to talk about the broadcast problem, okay? So this problem is actually motivated by the Byzantine generals problem, which is pretty old. And how does it work? So imagine like a war zone where there is a general and some lieutenants. And the general want to send a message to all the lieutenants. But the general doesn't know that some of them might have switched parties, okay? They might be collaborating with somebody else. So we want to make sure that if the general is honest, all the honest parties agree on the sent message. So they output M. But if the general is malicious, all the honest nodes should still agree on the same output. So this problem requires consensus among all the honest parties at all times. If the sender is honest, then everybody has to agree on the sent message. Otherwise, they still have to agree, all the honest parties, okay? And this problem has all sorts of applications, like in fault-tolerant distributed system, secure multi-value computation, blockchains, and so on. And there's a classical result which says that if all these parties have pairwise point-to-point channels between them, non-noisy, then you need at least more than 2 by 3 parties to be honest to realize this consensus. Which means that if you just have 3 parties and when any one of them can be malicious, it is impossible to realize the consensus guarantee. So in this talk, I'll be focusing on 3 parties, and we'll be using stochastic resources. What does it mean? So it could be correlated sources where all 3 parties get samples from a correlated joint distribution, or it could be a noisy broadcast channel. And by the way, this work can be thought of as one in the line of problems where we realize cryptographic primitives using stochastic resources. It can also be thought of as the one in line with information theory literature, where people have studied communication in presence of external adversary, like wiretap, AVCs, and so on, or even in terms of internal adversaries, like in network coding and so on. Okay. So the first problem is the one about Byzantine broadcast using correlated randomness. So there's a sender and 2 receivers, okay? So they have point-to-point link between them. On top of it, they also get IID samples according to some joint distribution. And the goal is to characterize the class of joint distribution which allow consensus and the ones which do not, okay? So there was a previous result from 2004 which claimed to solve the problem. So there is some condition on the joint distribution they gave and say that, okay, this is what is characterizing condition. But we found out that there was an issue with the condition and only one direction holds. So one of the things we realized is that by talking to each other, these parties can actually learn more about somebody else's joint distribution, even though they don't trust them. So there's like they can do some upgrades of their knowledge and build trust in some steps, which was not factored in the previous result. And this allowed us to characterize the sources which permit Byzantine broadcast. And this is actually a joint work with Professor Shun Watanabe, who's here. So you can look it up. Okay. So this is the last model I'll talk about, okay? So this is Byzantine broadcast using a broadcast channel. There are 3 parties. The guarantees are again the same, but the only resource they have is a noisy broadcast channel. And we want to characterize a class of broadcast channels which allow this. at the same time, we can also talk about a notion of consensus capacity here. So we want to use a noisy broadcast channel as a resource. And this is a one-way setup. These receivers, they don't talk back, right? There's only one direction of message. So we only need to consider a malicious sender. Okay. And yeah, this is the related paper. Okay, so what is a broadcast channel? It's a noisy channel, multiple receivers, and a single sender. Okay. Let us recall the common message problem where the sender wants to send a common message to both the receivers. So you want the receiver's output to agree on the sent message. Okay. What we are interested in is in the common message problem, but the sender is allowed to be malicious. This means that the sender may not send a valid code word, and it might send an arbitrary n-length sequence from their alphabet. Even in that case, we want to make sure that the receivers, they agree on what they output. So the malicious sender might send something in order to throw the receivers off. We want to still make sure that the receivers agree on the output. Okay. And when the sender is honest and sends a valid code word, we want the receiver's output to be the sent message. Okay. So this is setup. So you can define a code. It's an encoder and decoders. Right? And if the sender is honest, we want the decoders to output the sent message. If the sender is malicious, we want the decoders to still agree on what they output. Okay? And you can define the probability of error, which is the maximum of over 2 probabilities of error, the sender being honest and the sender being malicious. And you can also talk about what is achievable. So there exists a 2 to the NRN code such that probability of error goes to 0. And there is this thing called fast enough. I'll talk about it later. Turns out that in this problem, the capacity is sensitive to how fast the probability of error decays. This is like a very strange phenomena that we observe in this problem, but I'll talk about it towards the end. And we can talk about a Byzantine consensus capacity, which is the supreme of all achievable reads with consensus. Okay. So first of all, let's notice that the Byzantine consensus capacity is clearly upper bounded by the common message capacity, because this problem is same as the common message problem when the sender is honest. So you cannot do anything better than that, right? But turns out that it is there's a strict separation. It is not really equal to the common message capacity. Okay? And yeah, we talk about, the result handles all sorts of things. Okay. Anyway, so in the last 5 minutes, I'll try to talk about which class of broadcast channels allow communication with consensus and what is the consensus capacity for this class of channels. Okay. So let's try to answer the first question. When is it even possible to do it? Okay. So let's think about one use of the channel. And suppose the sender may send any input symbol. We ask, what random variables can both receivers agree upon? Okay. So let's draw a bipartite graph on the output alphabet of both the receivers, where I put an edge whenever a pair of symbols happen with positive probability under any channel input. Okay. So this way we can draw a bipartite graph. Now, this graph has various connected components. Okay. And note that the connected components, the identity of the connected component is something that both receivers agree upon, right? This is a deterministic map, which will map you from the output alphabet to the connected component number or whatever it is, right? So this means that we can think of a point-to-point channel from the input to this connected component alphabet, and this we call common channel. This is something that both parties can simulate at their own end. Okay, so so both parties agree on the common channel, right? And yeah, this can also be thought of as channel analog of GAC's corner common information for distributed sources because similar nature, right? All right, so we notice that both parties can agree on the common channel. What does it mean? This means that I can actually use the point-to-point code for the common channel. It's a point-to-point channel, right? And what would happen in that case? So when the sender is honest, both receivers can work with the point-to-point decoder and decode to the same message. So this case is handled. Now, over here, even if the sender is malicious, the sender sends something which is not a code word, the receivers will still receive the same VN sequence, and they are working with the same decoder. Oh, wow, what did I do? Okay. Okay, yeah. All right. So so even when the sender is malicious, the receiver still receives the same sequence, and they're using the same decoder. So whatever they output, it will still be the same. So this means that the consensus capacity is at least as much as the common channel capacity, right? And the question is it same as the common channel capacity? Can we do anything better? Turns out we can. So it is not the same as a common channel capacity, but it is still a characterizing condition in the sense that the consensus capacity is positive if and only if the common channel capacity is positive, okay? And in fact, actually, there is a strict separation. Consensus capacity is strictly greater than, there are channels in which it's like there's strict separation, okay? All right. Wow, okay. So over here, I just talked about one direction. And that is if the consensus capacity is positive, if the common channel capacity is positive, then the consensus capacity is positive. Let's try to talk about the converse, okay? Which means that if the common channel capacity is 0, we would like to argue that the consensus capacity is also 0, okay? So here is a channel for which the common channel capacity is 0 because there's only one component at the output alphabet. So in this case, I'll try to argue that we cannot send even a single bit without, a single bit with consensus. So what is this channel? The output at both the receivers passes through a BEC, binary erasure channel with erasure probability Q, and the erasures happen independently. Okay, so if we try to draw this sort of bipartite graph, it will be a single component. So the common channel capacity is 0 because the output alphabet is just one, a singleton, right? So over here, we'll argue that we cannot send even a single bit with consensus. For concreteness, let's think of the erasure probability to be half, okay? And we just want to argue, can we send a bit or not, okay? So suppose the code word for 0 is all zeros, and code word for 1 is all ones. Now, so this is a code word for 0, the probability, so the output should be 0 with high probability, right? And what happens if I just flip one bit? Well, if I just flip one bit, note that at the output, with the constant probability, both of them can be erased. So at the output, we cannot really tell, is it like code word for 0, or is it this specific sequence? So that and consensus will force us that it should not change by much. The output distribution should be like kind of similar. This, I'm not like saying it very clearly right now, but the reason is the consensus requirement and the independent erasures, which allow both of them to be erased at the same time. So that the output, we cannot tell whether it is like this specific sequence or this specific sequence, okay? So we can, what does it mean? This means that we can keep flipping one element at a time and accumulating these additive terms until we reach the code word for 1, okay? And when we reach the code word for 1, the probability that the output is 0 will go to 1 if probability of error falls faster than 1 over n, okay? Okay, so what did we show over here? We are saying that if probability of error falls faster than 1 over n, we cannot even send one bit, right? We cannot do any communication. Now, the question is, this converse requires probability of error to fall faster than 1 over n. Turns out it is not an artifact of the proof. And there are channels in which there is a single connected component, but you can actually provide positive capacity of consensus if you allow probability of error to fall slower than 1 over n. So this is not an artifact of the proof. And turns out the capacity is sensitive to how fast probability of error goes to 0 as n goes to infinity. On the other hand, the achievability we provide is with exponentially falling probability of error. And the capacity is defined with, so when I said fast enough, it is defined with probability of error falling faster than 1 over n. Okay, so with this, we covered the first question. Any channel with non-trivial common channel allows communication with consensus. The question is now, what is the consensus capacity of such channels? Okay. So recall that I said that this is a common channel problem, right? It's a common message problem. We want to send a common message to both the receivers. So turns out that we cannot work with all symbols of the input alphabet. And we define something called an effective input alphabet. These are the input symbols which can be distinguished by the output of the common channel. So for example, let's look at these symbols. So what is this? This is the distribution on the common channel on any input xi. Okay, so it's going to be a vector. So you can look at it in a simplex, right? And these two symbols, x2 and x6, they cannot be distinguished at the common channel because they give the same output distribution. So we will just pick one of them, and we cannot work with the other one. So there's only x2 here. Similarly, anything inside the polytop can also be written as a combination, convex combination of something over there. So it cannot. So it is also not part of the effective input alphabet. You can define it more formally. So turns out that the final capacity is actually same as the common message capacity, but instead we work only with the effective input alphabet. At the same time, there's also a further minimization of all possible attacks that the sender can do without getting noticed. So this is some kind of, it takes care of the malicious nature of the sender. So this is the consensus capacity. Now what is left? So all these results were for the case when capacity falls faster than 1 over n. What happens when it falls slower than 1 over n? We give an example where we show there's a separation. It can be different, but in general, we don't know what it will be. And the source model that I presented earlier was only for 3 parties. What happens when there are more than 3 parties? Similarly, we can also think of a channel model where in addition to a channel, there are also private links between the parties. Okay. Yeah, that's it. Thank you. I'm sorry, I'm excited. Yeah.
Thank you very much from Dr. Sangwan for her great presentation. Are there any questions?
Thanks for this very interesting talk. I have a question. Can you go back to the slide with this removal of the common, to this slide. So what are, so there the distributions which are distinguishable over the common channel remain, don't they? So shouldn't the distinguishability issue be already covered by just the computation of the mutual information?
Oh, you mean
I mean that
why do I
basically
need a further
things which are not distinguishable?
You mean why do I need a further minimization? Is that the question?
So it's just my intuition is that things which are not distinguishable don't count double in the, or don't, I mean, the distinguishability issue is already solved in the mutual information. So no, things which are indistinguishable just count as the same thing when computing the mutual information.
Yes, so that's what we are doing. By defining this sort of effective channel alphabet, we are only keeping the input, the elements of the input alphabet which can be distinguished.
Yeah, but what I mean is that they count, that by computing the mutual information, they count as the same anyway, don't they? Okay, yeah, okay, now I get it, because the output is of the original channel. Okay, yeah. Thanks.
All right, yeah. Also, the sender can still send anything, right? So we have to deal with all kinds of attacks that can be there.
Yeah, so now it's clear. Thanks.
Thank you for the talk and presenting so many different problems. I am curious about that multiple access channel where you said that you could identify the malicious
User.
messenger or receiver sender with an identification code there. I can see how, if if I understood correctly, I can see how you could aim to recover the information that the good sender, the honest sender is sending. I can understand how you could run an identification code with this logarithm of n extra elements, but I don't see how you could identify the malicious sender if he has control over what he's sending.
Right. So, so the model in which I use the identification code is called authenticated communication. Over there, we just need to flag there is an adversary. We don't identify who's the adversary. So the one in which we identify is a different model. Over there, I don't use identification code. Over there, we come up with a new code, which is kind of similar to AVC codes, but it's not ID code. With identification codes, we cannot identify.
Okay.
We can just flag the presence of an adversary or something.
Okay, I guess I mixed.
Yeah, I'm sorry.
Thank you.
I mean, it's too much, I guess.
Thank you again.
Yeah, thank you so much.